Hello, class. So this is going to be the final exam review. As with the previous reviews, I'll just do one video covering basically the things that I think are important from each section or things that I noticed that we struggled a little bit with. So I'll mention some of those things. And I'll go through the whole study guide since the exam mostly. Okay, so let me talk about the exam, I guess, first. As I mentioned in my message, or you can also see it in the announcements. If you go to announcement, it should be announcement that says final exam information. I think it's the last announcement. There's 16 questions in the exam, out of which 11 come from sections 4.9 and then 5.1 through 5.4. So most of the exam is from section from the sections that we've covered after exam 3, but there will be questions from previous exams because it is cumulative. So here are the topics that you'll be seeing. For example, there are topics from exam 1. There are topics from exam, so this is exam 1 topics, exam 2 topics, and then exam 3 topics. So I'll mention that just a little bit. For the most part, I already covered that, so I think you can just go back and look over that. Another thing to say about the exams that the format is going to be the same as exam 3. So we have 3 days, Wednesday through Friday of next week. And again, Wednesday at starting at 12 a.m. till Friday till 11:59, and you'll have 2 hours. I think it's for the final. I think so. You'll have 2 hours to do the exam on MyMathLab. Submit it. If you, have internet issues and you're taken out, you should be able to attempt the exam again. So hopefully that won't give us any problems with any sort of internet problems. Okay. So in terms of the exam, I think that's it for general things. As before, there's this you should be familiar with now. There's this formula sheet that you're going to be given. Okay, so other than that, I think we can just go ahead and start. So from exam 1, there's given a function f, calculate one-sided limits at a given point, x equals a, and use them to determine whether f of x is continuous. Identify points where f is not differentiable, find derivatives using the definition. So it's actually a lot. But hopefully you should remember, right? So for example, for finding the definition of continuity, a function f is continuous at x equals a, and then remember you have to check 3 things. One, check that the limit, so if limit as x approaches a of f of x exists, right? So the limit has to exist. And remember that for the limit, we had that this was equivalent to the limit as x approaches a from the left of f of x being equal to the limit as x approaches a from the right. So you check both limits, both two-sided limits, if they're equal and they exist, right? So then the limit exists. So this is where the one-sided limits might come into play. So if you have a piecewise function, so for example, if you have something like f of x equals x squared for x less than 2, then x for x greater than 2, and you want to find the limit as x approaches 2 from the left, then since we're working for values less than 2, right, the left of 2 is less, you'd be looking at this function. So this would be the same as the limit as x approaches 2 from the left of whatever function it is for x values less than 2, which is x squared. This is continuous, right? You can just plug in the value. So it's polynomial, you can just plug in the value for the limits, right? So this would be 2 squared, which is 4. So that's the first thing for continuity. The limit has to exist. Then, of course, the function value at that input has to exist. That's easy to verify. And then 3, let me say greater than or equal to. And then 3, the limit you found has to be equal to the function value. So really easy. If you do steps 1 and 2, you can just check if those things are equal. As soon as one of these first 2 steps isn't satisfied, then the limit does not exist. So that's the limit in continuity in one-sided limits. For differentiability, of course, there's different. If you have any edge like this, it's not differentiable there. So whenever you have an edge not differentiable, whenever you have some sort of vertical slope, so something that looks almost vertical, it would be not differentiable. And of course, if it's not continuous, it's not differentiable. It's kind of like the only three cases you have to worry about. Either a straight edge, right? And this straight edge could also look like this, right? As long as there's some sort of straight edge. Right? So any straight edge, anything where the slope seems vertical, because remember the derivative is the slope of the tangent line to at a point, right? So if the slope is vertical, it doesn't exist, right? Because you can't have infinite slope. And then of course not continuous. So this is for not differentiable. And then the other one, the definition of the derivative, just so you remember, the derivative at x would be the limit as h approaches 0 of this difference quotient, which this was used a lot, so hopefully you remember how to do this. So that's all from the first exam, it seems. Yeah, so that's the definition of the derivative. From exam 2, well, chain rule and implicit differentiation. So chain rule, hopefully you just have to remember the formula. You don't even have to remember because you're given the formula. You're given the formula, so it doesn't, yeah, here it is. You're given the formula. Whenever you have a composition, so f of g of x, say h of x equals this, you want to find the derivative. Well, it's simple. It's just the derivative of the outside, leave the inside the same, multiply by the derivative of the inside. So that's the chain rule that we've been using all this time, right? So hopefully that should be easy. Implicit differentiation is also something we've been using a lot. So say we have something like this and want to find dy dx. So the first thing you want to do, and it's not necessary, but I always like to do it, I assume y is a function of x. So and you kind of know that, so here you're being asked for dy dx, so you can kind of remember that by that, or you can just write first, assume y equals a function of x. Why you do that is so that you remember when you take the derivative of y squared, for example, to use the chain rule. Okay, so if we wanted to find dy dx implicitly, we'll take the derivative of both sides here. So d dx of e to the x plus y squared was d dx of 1. Here, okay, so we can split the derivative. Okay, so derivative of e to the x with respect to x is just e to the x. The derivative of y squared with respect to x, where y is a function of x, here you can just use a shortcut. Take the derivative of, so let me just write it like this. Take the derivative of this with respect to y, and just multiply by y prime. And that's a shortcut. And of course, the derivative of 1 is 0. And then if you want to solve for y prime, right, that's the same as dy dx. Remember, y prime and dy dx are the same thing. You'll solve for y prime here. So subtract e to the x from both sides and divide by 2y. So the only tricky thing here really is remembering that you want to treat y as a function of x, so you want to use this chain rule here. And then the shortcut in general is if you want to take d dx of y, where y is a function of x, so let's say some expression involving y, so let's say h of y, and this ends up being just d dy of h of y, so take the derivative of whatever expression of y you have, and then just multiply by y prime. And that's what we did here. So here h was y squared, right? H of y is an expression involving y, so y squared. Take the derivative of h of y, right, which in this case was y squared, that's this derivative, multiply by y prime. So we've done that a lot, so hopefully by now you get it, but that's the shortcut. Okay. So for example, if you had e to the y, where y is a function of x, and you want to find d dx, well, what would this be? Take the derivative of this as if it were with respect to y. So just derivative of e to the y with respect to y is e to the y, multiply it by y prime. So that's chain rule, that's implicit differentiation. Let's see, so that's from exam 2. From exam 3, so this is easy because we did recently, so how to find critical points, values of x and f of x, where f has absolute max and absolute minimums, intervals in which f is concave up and concave down. So we basically did an example of this, like all of the lecture for 4.3 was just one example doing all this. So definitely for this, go back to 4.3 and 4.2. The only thing I want to point out is something that we kind of forget, that I've noticed we're forgetting a little bit. If you have a function that is, okay, so actually let me write it like this. Suppose you're given a problem like maximize. So it's a problem we've done before, but let me just give you an example. Maximize a squared plus b squared, where a and b are greater than or equal to 0, and then a plus b equals 21, something like that. So there's basically two cases for problems like this. So either your function, which in this case, your function is going to be your objective function. Right? So remember, this is the objective function, which you'll be able to write as a function of one variable. But either, so let's say we solved for, let's say we wrote this as a function of one variable a, which you'll be able to do. So there are either two cases. Either f of a is continuous on a closed interval or not. On an interval, I already used AB, so let's use CD. It's either that case or not. Either f of a is not continuous, or f of a is not defined, the domain is not a closed interval. Meaning f of a is not continuous on its domain, and or its domain is not a closed interval. So these are the two cases. And I say this because in either case, you do something else. If something different. If you're in case 1, you use that theorem we saw in section 4.2, where you just look for absolute maximums and absolute minimums. And we went over this whole algorithm for how to do this. Basically, evaluate function at endpoints and critical points. And by the function, I mean the function, not the derivative. So evaluate function at endpoints and critical points. And whichever is the largest, that's the absolute max. Whichever is the smallest value you got from that, it's the absolute minimum. So that's in the case that you're in a continuous function on a closed interval. If you're not in that case, if you're in case 2, actually, let me do it in another color. If you're in case 2, let's do it in orange. Actually, it looks too similar. Let's do green. If you're in case 2, where you don't have a continuous function in a closed interval, then how do you maximize or minimize a function? Well, you just look for local max or minimums. And somehow justify why this is the largest function value or the smallest function value. And we did an example of that in the videos for this objective functions. I think it was section 3.11. Let me double check. Okay, so 3.11 is related rates. So that's not it. So 4.5, 6. Oh, I think it's 4.4. Yeah, so it is for 4.4. Yeah, so go back to section 4.4 for this. I went over examples of this. So definitely look at section 4.4. So let me make a note here. The last thing I want to say that we forgot a little bit, and I mentioned before already in a previous video, but I'll just restate it. So critical points are places where the derivative equals 0 or it doesn't exist. So if you have a function like f of x equals, or let's say the derivative equals x squared plus 1 over, see something that's not just a polynomial, yeah, over ln of x. This is the derivative already. So you want to find the critical points, then critical points are where this equals 0 or doesn't exist. So where f prime equals 0, you always remember, so that's good. You also have to remember that you also need to find where f of x doesn't exist. So actually, let me change this to an x squared minus 2. So what would be the critical points here? Well, from the places where the derivative equals 0, remember that's the same as the numerator equals 0, which is the same as saying x equals plus or minus square root of 2. Now, for when the derivative doesn't exist, now you're looking when the denominator equals 0, because that's the only thing that's going to make this function not exist, right? The denominator being 0. So when is ln of x equal to 0? Well, this happens when x equals 1. So these are critical points, and this is also our critical point. So that's just one thing to remember. You also have to check where the derivative doesn't exist. And that's for exam 3. So I went over these 3 things. I think I covered the things that we struggle with the most. Again, there's always these sample problems. Just go to your ebook on MyMathLab, go over those problems. Again, I always recommend going over the odd ones because you can look the solutions at the end of the book. So that's what I would recommend. So that's from previous exams. So let's go to the first part of the new material, section 4.9. So general antiderivative. So we use the notation, right? So if you want to find all antiderivatives of a function, just so we remember the notation, on an interval I, well, this is given by, notation-wise, the integral of f of x dx. Now, how do you find this? Well, first you find one antiderivative, just one, whichever antiderivative you can find. Remember, an antiderivative is a function whose derivative equals x. So a big equals f, sorry. So usually use capital F or capital letters for antiderivatives. So it's a function big F of x such that derivative of big F of x equals little f of x. So that's an antiderivative. And then once you found one of them, then all antiderivatives have the form big F of x plus c. So for example, you want to find all antiderivatives. Actually, let me use another color. You want to find all antiderivatives of x squared. Well, we know that one antiderivative is x cubed divided by 3. Let's just add 1 to the exponent, divide by the new exponent. And then that's one antiderivative, and then just add c to find all of them, where c is a constant. It's any constant. There are also initial value problems, meaning that you're given some condition. So for example, you're given solve f prime of t, let's say, equals t squared. And you're usually given an initial condition, so something like f of 0 equals 1. So this is an example that I did, I think, right at the end of 4.9, I did an example like this. But basically, you're looking for if you're given something like this, you want to find a function whose derivative equals t squared. Right? That's what it means when you solve an expression involving derivatives. This is what is called a differential equation. So here, you just want to find, actually, let me write it like this. Find a function f of t whose derivative is t squared. Right? So that's just finding an antiderivative, right? A function whose derivative is t squared, that's an antiderivative of t squared, right? So we already found one in the previous example. F of t equals t cubed over 3 works. And then, of course, we add constants, right? Because that's all antiderivatives have this form. Now, the way you get rid of this constant, c, is by using this condition. So what you want is that when you plug in 0, you get 1 into whatever function you found. So how do you do that? We'll just plug it in. F of 0 is going to be 0 cubed divided by 3 plus c. This should be equal to 1, and you can use this to solve for c. So c equals 1. So what's the solution to this initial value problem? And again, it's called an initial value problem because you're given this condition here. So the solution is f of t equals t cubed over 3 plus this constant that we found. You can verify that when you take the derivative of this function, you get t squared, and this function also satisfies the initial condition. That's basically how you work problems like this. It's just one extra step. Find all antiderivatives, use the initial condition to get rid of the constant. Okay. So that's that section. Okay, so now 5.1, where we did all of these partitions to estimate the area underneath the curve. So bounded by a curve in the x-axis using a Riemann sum. So that was, I think I did a lot of examples of that. Let's just do one simple one. Approximate something that's easy to. Okay, let's do something. ln of x on the interval. So 1 to 4. Using, so again, they're going to give you something like this. The function you want to approximate. So approximate the area bounded by ln of x. So by ln, let me just write it above, and the x-axis, meaning that we could have rectangles that go under the x-axis. Okay, so a function is said necessarily positive. In fact, no, let's just do it like this. Okay, on the x-axis on 1, 4, using, they have to give you the number of subintervals. Let's say we use 8 subintervals, and either a left or right. We also saw the midpoint, but I think this study guide only says left or right. So let's do using a right approximation. So right Riemann, or right endpoint approximation, which is the same as a right Riemann sum. This is the same as a right Riemann sum. So how do you do it? Well, it's always start with finding change in x. Remember, change in x was the length of each subinterval, and it's always the same formula. You subtract the endpoints of your interval and divide by the number of subintervals. So it's always subtract the endpoints divided by the number of subintervals. 4 minus 1 is 3, divided by 8 is 3/8. So that's the length of each subinterval. It's the first thing you want to do. Second, you don't have to do this, but I like doing it. You can find each subinterval, or just draw a number line, put your left endpoint, your right endpoint, and then starting with the left endpoint, just keep adding change in x every time until you get to the right endpoint. Or if you start with the right endpoint, subtract change in x as many times as you need until you get to the left endpoint. So for example here, we're at 1. When I get to the next endpoint, so I add 3/8. So remember, 1 is the same as 8. It's the same as 8/8. So 8/8 plus 3/8 is 11/8. When I get to the next endpoint, so I add 3/8 again. I'm always adding a change in x. So it'd be 14/8. When I get to the next endpoint, I add change in x again. So I add 3/8, 17/8. Next endpoint, I add 3/8 again. That's 21/8. Next endpoint, that's 24/8, which is, okay, so I need more space here. Oops. Yeah, because 24/8 is just 3, and I want to get all the way to 4. Just keep going. So plus 3/8 is 27/8, plus 3/8 is 38. But I did something wrong, right? Oh yeah, I did something wrong. Because this should add up to 32/8, which is 4. So 8/8 plus 3/8, that's 11/8. Plus 3/8 is 14/8. Plus 3/8 is 17/8. Plus 3/8 is 28. So that's where I made my mistake. So 28 plus 3/8, 23/8. Plus 3/8, 26/8. Plus 3/8, 29/8, and then I make it to 32/8, which is the same as 4. So you can always find all your subintervals like this. So this would be the first subinterval. Let me use a different color. This would be the second subinterval. This would be the third subinterval, etc. So you don't have to do this because we saw in the previous examples when I did over this section that all you need to do is find the first input, the first value you're going to evaluate in the first subinterval. So for example, in the first subinterval, since I'm doing the left endpoint, I know I'm going to start with 8/8, which is 1. And then just keep adding, you're changing x to that input. So what would be the left Riemann sum for this? Well, it would be, so remember, we're using rectangles to approximate. So the length of each rectangle is always changing x. The height is given by the function value evaluated at each endpoint. So for the first rectangle, we have, so changing x times f of, so what's the first input? That's 1. Okay, plus changing x, what's the second input? That's 11/8. Plus changing x, next input, 14/8. And how many times do you need this? Well, you need 8 terms in your sum, because so the number of terms you want in your sum is the number of subintervals you're working with, right? Because you're taking one input from each subinterval. So once you reach 8 terms in this sum, which I think the last one would be 29/8, so changing x times 29/8, this would be your approximation. So you just evaluate, plug in changing x equals 3/8, and evaluate the function at each input. Now, if you want to do a midpoint approximation, for example, what would you do? Like I mentioned, all that matters is the first value you're going to evaluate in the first subinterval. So we would want to find the first subinterval goes from 8/8 to 11/8. You would want to find the midpoint there. So what's the midpoint? How do you find that? Well, you just add the endpoints of your interval. So instead of subtracting, you add them and divide by 2. So this is going to be 14/8 divided by 2 is 14/16, which is 7/8. So that's right in between your interval, and that would be the first endpoint you're going to evaluate. Okay. So if you want to do this midpoint approximation, it would be changing x times f of the first input on the first subinterval. As we saw, that's 7/8. How do you find the other ones? Just add changing x to the input. So 7/8 plus 3/8 is 10/8, etc., until you have 8 terms in your sum. Okay, that's the idea. Then, of course, for right endpoint, you just go to, again, to the first subinterval, find the right endpoint. That's where you're going to be that's where you're going to be evaluating your function. So this was 11/8, and then again, just add changing x each time to your input to get to the next right endpoint. That's 14, etc., until you have 8 terms in your sum. Okay. That's how you do that. I did a bunch of examples of this, so you can go back to the videos on section 5.1 for that. Okay. Now, I also did stuff like this in section 5.2. Yeah, so here's 5.2. So let's talk about this. Calculate definite integrals using geometric formulas for area when the graph of f of x forms a triangle, a trapezoid, or part of a circle. So I think we did examples of a triangle and a trapezoid in section 5.2. Let's see. I'm pretty sure. Yeah, so it's in geometry. So here, for example, we did a few of these definite integrals. Remember, definite integrals is just finding net area. Okay? So any area that's below the x-axis, you count it as negative. Any area above the x-axis is counted as positive. So, for example, find the definite integral from -4 to 2 of 2x plus 4 dx. So I drew a picture of what this looks like. Right? So in orange here, we have the function from -4 to 2. Right? And you see the area we're looking for. The area in green below the x-axis is going to be negative. that I call that T1, that region T1. The area above the x-axis is going to be positive. I call that T2. Now, how do we find this geometrically? Well, we notice that both of these regions are triangles. So it's just the formula of a triangle. So for the area of T1, using the horizontal distance as the base, well, that's a distance of 2, right? -4 to -2, that's 2 points. So 1/2 base. What's the height? Well, we're going from 0 all the way to -4. So that's 4 units. And that gives you the area for that region. For the area for the top region, now we're going from -2 to 3 for the base. That's 5 units. Oh, which means that I did a mistake here. Yeah, so this should have been 5. Yeah, because that's 5 units, right? -2 to 3, that's 5 units. Yeah, so I did a mistake there. So that should be 5, not 4. And then the height, well, we saw here that it's 8, and you find that area. Now, what's the definite integral? What's the net area? Well, whatever's above the x-axis, which before we found to be 16, now we see that it's actually 4 times 5, which is 40. Uh, 20, sorry. Yeah, so whatever's above the x-axis, that was the area T2, we found had area 20, that's positive. Whatever is below the x-axis, which was this area, you add it as negative. So it's gonna, the net area is 20 minus 4, which is 16. We also did an example with the circle, right? Because we had this equation here, and I said, well, look at that, set that equal to y, and then square everything. And you see that you end up with an equation of a circle of radius 4. And then you realize, oh, this is just a fourth of the area of the circle, right? This region in green. So, well, the full area of the circle is pi r squared, divide that by 4, and that's the area of this region. And whenever you have something like that, something that looks like a constant minus x squared, if you're integrating that, say 0 to whatever this is, c, the x, always do that trick. Always set this equal to y and square everything, and you'll realize that geometrically you're just looking at a circle. It's centered at the origin. Okay. They also talk about trapezoids. So I actually don't know exactly what's the formula for the area of a trapezoid, so I'm gonna look it up. So it's similar to a triangle, I think. Yeah, so you have 2 bases. Okay, yeah, so let's do an example. So how do I, so let me just draw a picture. So because what you'll want to do is draw a picture, and if the thing looks like a trapezoid, and I'm sure you've done this in my math lab, then you would use the formula for a trapezoid. Let's say we're going from 1 to 4, or something that looks like this. Right, so it would be a trapezoid. And let's say it has a height here, so this is 5. So the height is 5. So this would be given by probably piecewise functions, right? But if you're trying to find the integral from 1 to 4, the definite integral from 1 to 4 of whatever this function is, when you write it out, when it's given to you, well, you would just have to use the formula for the area of the trapezoid. What's the formula for the area of the trapezoid? It's a plus b divided by h. What are a and b? Well, the horizontal sides are a and b. Doesn't matter which one is which. So the flat sides that are parallel are a and b. Oh, so I need to give you what a is here. I didn't give you. Let's say this length is 2, and h is the height, and this is the just this height here, right? So not this distance, because this distance is going to be greater if you're trying to find what that side is. It's just the actual height. So how would this be using the formula here? So a I gave you to be 2. B is this bottom distance, which we see is 4. The height is 5. So it would be 6/5. And those are the only 3 examples that they mentioned here. Either triangles, rectangles, triangles, I guess you could do rectangles, right, and squares, because that's just like one length times the other length. So one side times not the opposite side, but the other side. Or circles, right? Circles, trapezoids, triangles, squares, and rectangles you should be able to do as well. That's the idea. You could also do this by separating it into triangles. You know, this is a triangle, this is a triangle, then this is a square, whichever way you want. So I'm not going to say much more about that. Just definitely look over the examples in section 5.2. Fundamental theorem of calculus. This is the one of the most important things, right? The part 2 is that whenever your function is continuous, you can just evaluate using this antiderivative method. So suppose you want to find the integral from, let's do negative pi over 2 to pi over 2 of 3 cosine of 2x dx. The only thing you have to check, this is your function of x, whatever's inside between the integral sign and the dx. And also, please always write dx. If you haven't evaluated the integral yet, always write dx. You're gonna get points off if you don't do that. So always write dx. If the variable is t, write dt. If the variable is l, write dl. But always write that. So the only thing you have to check is f of x continuous on this interval on negative pi over 2 to pi over 2. That's the only thing you have to check for the fundamental theorem of calculus part 2. In this case, it is, right, because cosine is continuous everywhere. So what does the fundamental theorem of calculus say? What is this going to be? Well, all you need to do is find one antiderivative of this function f. And remember the notation, evaluate at the endpoint. So let's find one antiderivative. Okay. So we know that something that's going to look like cosine 2x is sine 2x. Oh, and by the way, we can make this easier. We can just move the constant outside. So remember, there's all those properties we saw about integrals. You can separate it as sums and differences. You can move constants out. Right? So those are the two main ones. So moving the constants, so really we just need to look at antiderivative of this. We know it has to look like sine of 2x. Then usually the way I did it was I let f of x be a constant times sine 2x. Take the derivative. We bring the 2 outside. Leave the inside the same. That's by the chain rule. And then we want 2c to be equal to 1. Because here there's a constant of 1, so c has to be equal to 1/2. So f of x has to be 1/2 sine 2x. The other way to think of this is, I know that when I take the derivative of sine 2x, I'm going to get a 2 outside. I want to get rid of that 2, so I have to multiply by 1/2. But anyways, so here there's going to be a 3 then multiplying, because I move the constant out. Once you find an antiderivative, then just evaluate at the endpoints. So it's going to be 3, and just worry about the constant at the end. Big F of x is 1/2 sine x. Evaluate at the upper endpoint, right? So at pi over 2. Then you subtract what the function again, the antiderivative, evaluated at the bottom endpoint. Oh, and there's a 2 there. Yeah, forgot the 2 there. Okay. Now what is it simplify to? 3 times 1/2 sine of pi. 2 times 2 is 1, minus 1/2 sine of pi. Sine of pi is 0. 0 minus 0 is 0. 3 times 0 is 0. So again, let me specify here, always write dx until you get to this step. Once you write it in this step, once you've taken the antiderivative and you're going to evaluate, you don't need the dx anymore. Anytime before that, you have to write the dx. Okay. then yeah, as long as your function is continuous, just find an antiderivative, evaluate at the endpoint. Of course, I went through an example. For example, this thing here, you can't use the fundamental theorem of calculus because if you check if f of x equals 1 over x is continuous on the interval -1 to 1, you find that it's not. So you can't use the fundamental theorem of calculus. So we don't know how to evaluate this interval yet. You'll learn how to do this in Calc 2. So if you're given something like this in the exam, you would say, can't use the fundamental theorem of calculus because it's not continuous. And remember, FTC for fundamental theorem of calculus, because f is not continuous on -1, 1. And here I can just write f because I called f 1 over x. If you don't label f as 1 over x and you just write f is not continuous, the grader might be confused. So either just use 1 over x here, or first write f of x equals 1 over x. And that's the fundamental theorem of calculus part 2. It's very easy. As long as you know how to find an antiderivative and your function is continuous in that interval, they're very easy to evaluate. Okay, so that should be 5.3, the first part. Now, of course, we also did examples evaluating taking derivatives. So using the fundamental theorem of calculus part 1, so an example of this was find the dx of the integral from -1 to 1 of t squared dt. What did the fundamental theorem of calculus of 1 say? As long as this function is continuous on the interval -1 to 1, this whole thing is continuous and differential on the same interval. So here you also still have to check that t squared, whatever function is inside, is continuous on -1 to 1. If it is, which t squared is, then what's the derivative here? I want to make this an x. Yeah, so remember that the variable in this case is the upper bound, or the upper endpoint of your interval, the right endpoint of your interval. That's what changes in this function. But remember, this is the area function. Right? This whole thing in red is actually, let me do it in blue. This whole thing in blue is the area function as we defined it. So in the area function, what's changing is how far of the interval we're calculating the net area. Right? So if this is 2, we're calculating the net area on the interval -1 to 2. If it's 5, we're calculating the net area on the interval -1 to 5. But anyways, whenever you have this setup, as long as your function is continuous on that interval, which should be x, t squared is a polynomial, it's continuous everywhere, and this just replace the t's with x, this would be x squared. Another variation would be something like this. And here again, you first check that t squared is continuous. Which it is, right? It's a polynomial. And then what's the trick here? Realize that this part here is not the area function, but the area function composed with cosine. Right? Why? Because you see the input is not x, it's cosine of x. So it's a composition. So when you want to find the derivative, you need to use the chain rule. Take the derivative of the outside, leave the inside the same. That's the derivative of the inside, which is the derivative of cosine. So let me not write it like that. Let me write it like this. Right. What is this equal to? Well, we know what a prime is of x. Right? Just replace the t's with x. We found that here. And so yeah, just whenever you want to find a prime of something that's not x, but an expression involving x, first find a prime of x. So first find, and then just a prime of x, and then just replace the x with cosine x. So a prime of x, we already saw was x squared. We replace the x with cosine, so this becomes cosine squared x. Since the derivative of cosine, which is negative sine. So there's a negative in front, we get sine. That's the fundamental theorem of calculus part 2. Now, another variation you could see is something like this. Actually, let's do it a little bit different. Let's do so actually I don't see if you see a variation like this. So actually, let me not talk about it. If you see a variation where both endpoints are functions of x, then you probably must have done that in MyMathLab. I would refer to that. I didn't see one in my notes, so just in case you didn't see it, I'm not going to talk about it. The last thing which we saw in the last section, 5.4, was just very easy, mean value theorem. And this was pretty straightforward. If you know how to find a definite integral, you know how to find the mean value theorem, the mean value of the function. And then from that, you can do the mean value theorem. So first, let's say find the mean value of f of x equals 1 over x on the interval 1 to 2. Actually, let's do 1 to e, so it simplifies a little bit. So if you remember, what's the mean value? Oh, it's not called mean value, it's called average value. What's the average value? Well, it's pretty straightforward. The average value is going to be, just take the integral, the definite integral, like you would always do it, of your function. The only thing is that you divide by the length of the interval. So what's the length of the interval? You subtract them, so e minus 1. And this is going to give you the average value. And here, of course, we did an example like this, right? We know that an antiderivative of 1 over x is ln of x, right? Because the derivative of ln of x is 1 over x. Whenever x is positive. When x is negative, again, something else happens. For now, don't worry about it. So an antiderivative would be ln of x, so this would be ln of x. Remember the notation, evaluated from 1 to e. So ln of e, so evaluate at the top endpoint, subtract evaluated at the lower endpoint. Ln of e is 1, ln of 1 is 0, so it becomes e, 1 over e minus 1 times 1, which is just this. Okay. Then what did the mean value theorem say? If your function is integrable, right, it's the same as continuous, on an interval a, b, then there exists a c inside this interval such that the function value, so don't confuse this with the mean value theorem for derivatives, the function value, not its derivative, just the function value of c equals this mean value. Remember, this is the average value of the function, so equals the function, the average value. And of course, we did an example of this in section 5.4. Where is it? Yeah, so here it is. Yeah, use the mean value theorem of integrals for f of x equals e to the x of 0 to 2. So we basically, you just want to set up this equation. F of c equals the mean value or the average value, and then just solve for everything. Simplify everything and solve for c. So in our case, we had that there exists a c such that f of c equals the e minus 1 integral from 1 to e of 1 over x dx, right? This is by the mean value theorem. 1 over x is continuous on the interval 1 to e, so that's the only thing you have to check. So then just plug in everything. F of c f is 1 over x, so this part is going to be 1 over c. This part we found, this whole thing simplified to 1 e minus 1, and then you solve for c. You solve for c here, you get c equals e minus 1. And that's the value such that when you plug it into the function equals the average value of the function. Now, I think that's about 50 minutes. I think I covered all of the big parts of the important topics. Now, of course, always remember, you can always practice these values, these examples. I'll be in the Kasem tomorrow from 10 to 12. And then, so our final starts on Wednesday. So probably what I'll do is I'll have office hours Monday, Tuesday, Wednesday from 12 to 1. And then Thursday, I don't know if the CASM schedule changes. If it doesn't, or if I'm not tutoring, I'm gonna go all the way to Thursday 12 to 1 as well. If not, I'll do Thursday 10 to 12 like usual. But I'll make an announcement about this, so don't worry too much about my office hours. I'll post it, and I'll make sure that there's enough time for you to contact me if you have any questions. Okay. This is the review. I think this exam should be one of the easiest ones. It's because I think the new material, the integrals, is not too bad now that we know the fundamental theorem of calculus. And I think the previous things that come into this exam are things that we've been doing a lot, like implicit differentiation, chain rule. We use that a lot, right? We did a lot of examples finding local maximums and local minimums, absolute maximums and absolute minimums. So I think it's going to be good. So just study. If you have any questions, just let me know.